want to take just a few minutes and talk about a good process that works well with me when in doing force problems. A lot of this is common sense. A lot of this is just simply steps that you really just have to do, and I've just kind of simplified the process down a little bit. The first thing that you need to do is draw the free body diagram. Now, I go a little bit more than the typical free body diagram that just includes the forces. I include all the information from the problem. Masses, any forces, weights, pulling forces, angles. I include all that type stuff. Essentially, I use the free body diagram in place of the problem. I take the words in the problem and the free body diagram illustrates it. A couple of things to remember: that the force due to gravity is always directly down. Friction, if friction is present, is opposite the direction of motion or the direction the object wants to go, such as for static friction. The normal force, always perpendicular to the surface. A lot of times the kids will just say the normal force is up, and I'll go, no, it's perpendicular to the surface. In doing the problems, be very careful when you're given the mass and the weight of the object. Two completely different things. I include both in my free body diagram, but be careful with those terms. The second thing that I like to do is I like to set up the XY coordinate system. This is a little bit of a, sometimes a lot of the kids think of it as what's the point in this? That seems kind of silly. And it does, but it helps me visualize breaking up the vectors. Generally, the x-axis will be parallel to the surface that the object is on. That's how I set them up. You don't have to do this. If you want to make it more difficult, then don't do it that way. But this makes the problem easier. If the object is not on a surface, like it's a sign that's being hung, then just use regular positioning, which is X is horizontal, Y is vertical, that type of stuff. You can tilt, you can rotate the XY axis as much as you want, as long as you don't change their relative positions. I mean, you still have to follow the right hand rule, but you can tilt it, and you can have the positive x-axis pointing to the left and the positive y pointing down if you want. It's all relative. That's the nice thing about this, and sometimes that's a little bit challenging for kids to understand. But the reason I sketch it out is to help visualize breaking up the vectors a little better. This is nothing that you have to do, but this is something that I like to do. That when I set up the diagram and when I set up the coordinate system, that if the box is moving, it's moving in the positive x direction. That just tends to make the problem a little bit easier for me. You don't have to do it that way, and then I'll explain later on why I do. But that does make it a little bit easier. Here's one example of one of my free body diagrams on a problem, and you can tell I get into a lot more detail than the typical free body diagram. I just did air quotes when I did typical. When I said typical free body diagrams, I don't know why I did, because you couldn't see that. But anyway, you see I got the angle. The inclined angle is 12 degrees. I have actually this force, the gravity vector, broken up into its components, which you're not really supposed to do, but I do to help me understand the problem better. I have forces written in there. Here's how I have my XY axis tilted. In this particular problem, the box is being pulled up the incline into the positive x direction. Here's another incline problem where the box is going down the incline, and so I flip the incline so that it's still going in the positive x direction. Step number 3. Set up the force table. Basically, I'm taking each force from the free body diagram and breaking it up into the x and y components. Did this with vector projectile motions all the time. This is nothing different. The big thing that a lot of kids sometimes forget to do is if they have three forces in the free body diagram, they better have three forces listed, no more, no less. And sometimes they miss that, and you just have to be careful when you're doing that. Account for all your forces. You have to be careful when you're using sines and cosines. Like with projectile motion problems, the x component typically tends to be the cosine of the angle. This is not the case with force problems, especially when you're looking at inclined planes. You have to be very careful when you're breaking up the forces, and you have to understand the sines and cosines. Sine is opposite side over hypotenuse, and the cosine is adjacent side. Step number 4 is probably one of the easier steps, but probably also one of the more confusing steps, and that's determining the net force. Basically, you want to determine what the net force in the x and y direction would be. For example, if the object is in equilibrium in that direction, then your net force is 0. All your x's or all your y components are going to add up to 0. If it's not in equilibrium, if it's accelerating in that direction, all those net forces add up to ma. Keep in mind, equilibrium means all the forces are balanced, which means no change in velocity, which means the object is at rest, or it's moving at a constant velocity, a constant speed. And it just kind of occurred to me, this whole process can also be used when you're doing centripetal motion problems and breaking up the forces, and all the forces, like in the x direction, might add up to ma, where a is the centripetal acceleration. It works just as well there too. Step 5 is you basically do the math. Steps 1 through 4 are all the physics behind the problem. Step 5 is the math. I don't use my calculator until I get to step 5. When I'm breaking up the forces in the force table, I don't use a calculator. I just write them out. The force times the cosine of the angle, whatever. And basically, at this point in a lot of the problems, you're simply solving for what the problem is asking for. A lot of times you're going to have to do an intermediate calculation, like solving for normal force. Okay. But you're just adding up all your y's, and you know what that equals to. Solve for what you don't know. When you're doing these problems, it's important. Keep your work organized. These can get a little bit lengthy, and it cannot be graded if it cannot be read. So keep all the work organized. Find a system for doing these problems where it's neat, it's correct, and you're showing all your work. These are the 5 steps I take my students through, and as we're going through a problem, if they're having stuck, I kind of reiterate these steps with them and find out where they skipped a step, because typically when they make a mistake, they've skipped a step. Well, that's all I got for you. Hope this has served you well. Thanks.